to the second day of the microstructure conference. It's our pleasure to have Yiming Chen from Stanford, who will be telling us about BPS chaos. And then we'll have many questions and hopefully many discussions.
Okay, thank you. Thanks for putting this event together and inviting me to talk. So I was assigned with the task of talking about this paper last year that I wrote with my colleagues Henry Ling and Stephen Schenker. So the plan of my talk today is the following. So for those that have not heard me or anyone talking about this paper before, I will give a brief review about this idea of what we meant by BPS chaos. So it's a particular generalization of ideas in quantum chaos to the BPS context. Then I will provide a brief review of some gravity computation, which suggests that for supersymmetric black holes that have macroscopic horizon, applying this prescription of BPS chaos, one will find that these supersymmetric black holes have very strong chaos in a sense that I will make precise later. And then I will talk about some sample calculations that we did in various field theories, where we were only able to do these computations in cases without macroscopic horizons. So some cases that we were able to study are half BPS states in D1, D5 CFT and half and quarter BPS states in the n equals to 4 Sylvian Mills theory. So because I know people here are probably more interested in the first case, I added some more slides and maybe focus on the first case more. And in the end, I would conclude with pointing out some open problems. So some things I won't talk about today due to the lack of time is that I think there is very interesting parallel story that is happening about this classification of BPS states in terms of fortuitous and monotone. And there is a very close connection between what I said today and what is going on there, but I won't talk about the connection. And we had a paper with Yiming, Bigson Shen, and Zhenbin Yang on using some SYK toy models to illustrate many of these ideas. So if you are interested, I refer you to this paper later last year. Good. So let me start with some general motivations. I think because we're all here, we all agree that trying to understand properties of black hole microstates, and in particular, how to describe them using language of string theory is a very important question. Now, let's say we have some proposal for what the microscopic description of the black hole is. One would like to have some quantitative way to measure how much it really captures the desirable feature, physics of black holes, which should include, but more than the entropy. Now, of course, well, this is a difficult problem, so such measures might well be very difficult to compute in practice, but I think as a first step, we would nonetheless like to have such a criteria or measure of how they resemble black holes, even as a matter of principle. Now, in non-BPS settings, ideas from many-body physics like thermalization and quantum chaos have provided many useful measures for whether quantum states resemble the feature of horizon. For example, here I just listed some well-known things like exponential decay of two-point function, and consider out-of-time order correlator, which should exhibit this maximal Lyapunov exponent when you have a horizon. And as a more fine-grained feature, you should see this linear ramp in the spectral form factor. So many of these are what we have in the non-BPS settings. However, generalizing these ideas to the BPS context where we don't have an obvious sense of time evolution because everything is, all the states have the same energy, generalizing these ideas is not very straightforward, despite the fact that we have much more analytic control in the BPS context. So the goal of my talk today is to discuss one applicable notion of chaos in the BPS context, and I will discuss its application in gravity and also in simple field theory examples. Good. So now to begin introducing this idea of BPS chaos, let me first review a little bit of various different notions of chaos. So given a quantum system, the oldest and most well-known notion of chaos is what I refer to as the eigenvalue chaos here, which is simply the fact that for a quantum system with discrete spectrum, you have many, many energy levels. And then for a system exhibiting chaos, there exists this universal random matrix statistics among the energy levels. So I will go into that in more detail later. But this particular notion of chaos does not apply for BPS states, because here, as I drew here, for the BPS states, all the states are constrained to have the same energy because of the BPS condition. So simply the supersymmetry forbids the states to have any spacing. So you cannot talk about the random matrix statistics of these states. Oops. Now, there is a closely related but different notion of chaos, which here I refer to as eigenvector chaos, which is not to focus on the energy eigenvalue itself, but instead focusing on what the eigenstates look like. Okay? And the idea is that with respect to a set of simple operators in your theory, the eigenstates, the wave functions, they resemble random vectors. So the wave functions are very complicated. They resemble random vectors. And the way to quantify this statement is usually phrased in terms of this eigenstate formalization hypothesis, which says that if you choose a simple operator O and look at its matrix element between two energy eigenstates, EI and EJ, up to a smooth piece that is proportional to the identity, some smooth function f times the identity, you will have these tiny but highly fluctuating terms that is exponentially suppressed e to the minus s over 2 times a matrix Rij, which to a very good approximation is a random matrix. Now, this idea of how eigenstates resemble random vectors, we can apply this idea to the BPS subspace as well, just with a minor modification, in the sense that in the BPS subspace, we are not talking about a single eigenstate anymore. We're already talking about degenerate subspace of eigenstates. So the correct notion is really a random hyperplane or random subspace of states. Now, this idea was used by Lin, Maldacena, Rosenberg, and Chen in nice papers in 2022, where they propose this as a criterion for how we can define the chaos for the BPS subspace. So we refer to this as the LMRS criterion. So the idea is the following. We again choose some simple operator O, and then we sandwich it between the projection operator into the BPS subspace. So here these are the BPS states. I'm defining a projection operator P BPS as the projection into that subspace. So I define a projected operator O hat as POP. Okay? And now if you look back into analog of this eigenstate formalization hypothesis, once you project into the BPS subspace, if the BPS subspace resemble random subspace, you should expect that the projected operator up to an identity piece, which we can subtract off, just should look like a random matrix. So that's the main idea here. We will simply define the chaos or call the BPS subspace as chaotic when the projected operator O hat shows random matrix behavior. We will quantify this statement more later, but that's how we define the chaos of the BPS subspace is through projecting the simple operator into it and see whether the projected operator behaves like a random matrix or not. So what do I mean by simple operators? I think this is a question that is clear in usual many-body physics settings like lattice models and simple toy models. But in these holographic field theories, I think a rule of thumb for choosing simple operators is just to choose operators that correspond to light supergravity fields. So these are some, let's say, some primary operators which have scaling dimension that is order 1 in the strong coupling limit. Or more, so these will be usually some BPS operators whose scaling dimensions are protected. But more generally, one can also consider some composite operators, let's say some product of these simple operators, which are non-BPS. So this will be some choice of simple operators that we will work with, and I will provide some explicit examples later in the talk. Now, once we have this projective operator, we need some ways to tell whether it looks like random matrix or not. So as you probably know, that a simple way to tell whether O hat, this projective operator, exhibits random matrix statistics or not is to look at the nearest neighbor spacing in a spectrum. So now, because I have some operator with a non-trivial spectrum and generally it's discrete spectrum, I can just list the eigenvalues and compute these nearest neighbor spacings and look at a histogram. So it's, as I briefly mentioned earlier, it is well known that the chaotic systems and integrable or non-chaotic systems behave very differently in terms of this histogram. The chaotic systems, the eigenvalues have vanishing probability of being very close to each other because of this effect of level repulsion. So there, the histogram or the probability distribution should start at 0 and then rises and eventually decays to 0. So that is the famous Wigner surmise for the distribution of level spacing, and it reflects the underlying level repulsion between eigenvalues. Now, in an integrable and non-chaotic system, there doesn't exist this phenomenon of level repulsion, and you can basically think of the eigenvalues as just completely random. But in that case, generically, the distribution for the spacing follows a Poisson distribution. So it starts out as some big value and then decays to 0. Now, for our purposes, this notion of chaos using just the nearest neighbor spacing is a little bit too weak. It's not fine-grained enough. So why is that? The idea is that the level spacing only probes the existence of chaos at the finest possible scale, because you're only looking at whether the level repulsion exists between nearest neighbors or not. But there is an idea coming from quantum chaos that one can improve this criterion by quantifying the quality of chaos by looking at how far this effect of level repulsion propagates in the spectrum. So the idea is that you have many eigenvalues. Eigenvalues at some location does not just have repulsive force on the nearest eigenvalue, but the repulsive force propagates propagates along the spectrum up to some energy scale, which is usually referred to the so-called Thouless energy scale. So to be more precise, the Thouless energy scale is defined such that, for example, for GUE for systems in the GUE universality, the density correlation, so the fluctuation in the spectrum, should follow the famous sine kernel formula as long as the difference between the two eigenvalues are smaller than the Thouless energy scale. Okay. So that's how it is defined. Now, when the two eigenvalues are more separated, it could just be they are not correlated, or they could be correlated in some completely different ways. So, but that would signal the deviation from the random matrix universality. So basically, yes.
What is L in this formula?
Sorry. So here, L is the number of eigenvalues. It's the size of the matrix.
Okay, thanks.
Right. So here I'm normalizing things in such a way that the total span of the spectrum is order 1. Right, and the spacing is of order 1 over L. Good. Now, just to give you some examples, if you really consider a pure random matrix, like a matrix, typical draw of a matrix from the Gaussian, let's say Gaussian unitary ensemble, you will find this famous semicircle distribution of eigenvalues. And in this case, the Thouless energy is really just order 1 because it's like the most chaotic possible case. So order 1 means what we really mean is that the Thouless energy is order 1 compared to the total span of the spectrum. So I normalize my span of the spectrum as order 1, then it means that even the eigenvalue at the left end would have some repulsive force following the universal formula to the eigenvalue on the right end. On the other hand, we will call the system that we will define the notion of weak chaos when in a large N system, the Thouless energy scales as inversely as powers of N. So it scales as 1 over N to some power, which goes to 0 in the large N limit. So here, the idea is that this idea is mainly coming from intuitions in many body physics, where if you have some weakly interacting quantum system, then generically the Thouless time is inversely, Thouless energy is proportional to the powers of your interaction coupling. So in a large N system, the effective coupling is the Newton's constant, which is 1 over N to some power. So we would expect that if we would define the notion of weak chaos to be that the Thouless energy simply scales as powers of this interaction strength, which is 1 over N to some power.
Can I relate this to some notion of the relative size of the off-diagonal matrix elements in some suitable basis? Like how rapidly things are mixing with each other?
Yes, I will talk about that in a moment. Yes, I will give you an example exactly of that time. Good. So let me just, because some of these notions might not be very familiar to some of you, let me just make some more comments on that. So practically, to study this Thouless time is more convenient to study really the inverse of, sorry, I misspoke. We want to study this Thouless energy, but sometimes it's more convenient to study the inverse of Thouless energy, which is also called the Thouless time or the ramp time, which can be extracted using this nice quantity called the spectral form factor. So in our context, the spectral form factor is simply defined as the trace of e to the I O hat t, the square of this quantity. So you can also write it in terms of integral of the spectral density. Now, what happens in the spectral form factor is that the universal sign kernel translates to a linear behavior in the spectral form factor. So at late time, where the sign kernel is a good description, you should find linear behavior where SFF is linear in T with some universal coefficient. But at early time, the SFF can do various different things. Now, if you really look at the random matrix, pure random matrix, the SFF, after the initial decay, it immediately transits into the linear ramp at order 1 time. So this is the same as the statement that the Thouless energy is order 1 in this case. And we will call these as strong chaos. While in a weakly chaotic system, the SFF does not immediately transit into a linear ramp. It does various different non-universal things before this time scale, which usually scales as polynomially in N. So it's some very long time scale where it transits into the linear behavior. Good. So let me provide some more intuition about this Thouless time. So how do we really think about the Thouless time? What really determines it? Now, to discuss that, let me back off a little bit and went back to the non-BPS case where we actually have a better understanding of what the Thouless time is from many different perspectives. So there, what we are looking at is the spectrum of the Hamiltonian itself. And for that, we can just look at the standard spectral form factor defined using the Hamiltonian. So we have the same formula, just O hat now is just given by the standard Hamiltonian. And in this case, there is, in fact, a universal formula for what the Thouless time is, which you can derive from gravity, but also from many body perspectives. Roughly, it tells you that, let's say we are focusing on this quantity in some energy window, which corresponds to some black hole. The Thouless time, the time scale where you should expect linear ramp, is inversely proportional to the imaginary part of the quasi-normal mode frequency on the black hole background. So here, omega quasi-normal mole is the lowest quasi-normal mole frequency on that black hole background. So this means basically something that if you have some long-lived modes on that black hole background, some modes that does not thermalize very quickly, some modes that stays outside the horizon for a long time, that will lead to a long Thouless time, right? Because those modes will have very small imaginary part of the quasi-normal mole frequencies. So in this non-BPS setting, we have this very clear intuition that if we have some long-lived modes in our systems, that would lead to long Thouless time. And there's a quantitative way of saying that. Now, for example, just to build more intuition, for one-dimensional many-body systems, if the system has size L and there is a diffusive mode, let's say at late time the model is governed by some hydrodynamics, and there's a diffusive mode, then the Thouless time scale will essentially be squarely so L squared divided by the diffusion constant. So L squared because diffusion you need time that is of order a system size squared to diffuse to the entire system. Now, in the BPS context, coming back to the BPS context where we instead of Hamiltonian, we already have this projective operator. This time that we have here in the expression is not the physical time that we use to evolve our system. This is some auxiliary time that we introduced in the BPS subspace. So we do not really know a formula that is as simple as the non-BPS case. However, this notion of long-lived modes lead to long Thouless time, this intuition still carries to this case. So coming back to Emil's question, so here, one particular example that is illuminating and also very useful in our later discussion is when this projective operator is a banded random matrix. So it would be a special case where it's a matrix where it only has non-zero elements very close to the diagonal along inside a window of width W, but elsewhere the matrix elements are all zero. So this is called a banded matrix. Now, of course, one can relax a little bit and make the off-diagonal elements non-zero but small. That would be more like what Emil was asking. But this would be an extreme case where you only have non-zero elements within some small width W. Now, a banded random matrix is defined as a matrix where within this width, within this band, you just take all the matrix elements to be IID random numbers. So that's what the banded random matrix means. Now you can think of this matrix as defining a hopping model in a one-dimensional lattice, where the hopping terms have some finite range. So at one side, it can hop to a site that is W distance away, but the hopping amplitude is random. So it's some random hopping model. And these kind of hopping models have been studied in the literature. And the idea is that excitations on this one-dimensional hopping model, they diffuse. So it takes some time for them to diffuse to the entire system. So this notion of a diffusive motion provides an intuitive way to understanding that the Thouless time of such a banded random matrix will actually be long. So it takes some time for local excitations to diffuse to the entire system. And it is known that the Thouless time of such a random matrix would scale as L divided by W squared. So again, it's L squared because of this diffusive feature. So it's the ratio between the total size and the width, the square of that. Now, this result that I just said here, there have been some rigorous proof by many authors, but the rigorous proof have some restrictions, basically that the proof only works when L and W scales in certain way in the large L limit. So I didn't write down the restrictions here, but you can find the detail in the citations in our paper. Now, one can try to study this banded matrix numerically, and numerical support this formula more generally for more general choice of width versus L. Now, I think it'd be fun to point out that this is a hard math problem, and it's actually an active area of math research to quantify the chaos of such banded matrix. And here is a talk by Terence Tao that happened earlier this year, where he was talking about these banded matrices. And soon we will see that these banded matrices show up in fastballs, which I find very interesting. Okay, so now let me briefly review a little bit of what LMRS did in their paper. So they did a computation using gravity. So I think probably many of you have not seen their calculation. So let me just give you some flavor of what they did. So the idea is that for macroscopic supersymmetric black holes with an ADS2 throat, the low energy physics contains a particular softmos corresponding to the length of the throat. So the length of the throat is very long and it has large fluctuations. Now, an effective theory of this softmos, which is called the Schwarzian theory, as well as in the supersymmetric context, is supersymmetric generalizations, have been studied and applied to BPS black holes in various UV complete theories. So I think many of you, including me, were there when Matt Hademan gave a nice talk in 2022. So I refer you to his talk to learn more about this Schwarzian theory. Now, LMRS studied what this Schwarzian theory says about this quantity, this spectral form factor. So let me very quickly tell you roughly how they did the calculation. So let's first try to understand how we represent this projected operator O hat in the Schwarzian theory. So it's simply that you take some simple local operator O, and then you sandwich it with a projection, but it is more convenient to think of the projection as simply infinite Euclidean evolution. So you sandwich with e to the minus infinity times the Hamiltonian, and that can be pictorially represented as you have some operator O here, and here on both at both ends of this operator, you attach it with some Schwarzian boundary with infinite proper time. And then in the bulk, this operator O sources some word line of particles that is tense. So it's just some diagrammatic way of representing the same quantity that I wrote here. Now imagine you want to compute a quantity that is trace O hat to the power k. Then what you would do is simply to take k copies of this figure and join them together. So between any of these two red dots, there's a, even though here it looks finite, but what we really mean is an infinite Euclidean evolution between any two of them. And then there are these legs extending out of these operators, right? Then following the idea of holography, one can look for whatever the bulk solution is to fill in the boundary condition, and then we connect these lines in various ways. Oops. Okay, good. So LMRS studied this connected contribution to this correlator, trace O hat to the M and trace O hat to the N. And following standard JT gravity ideas, here what you have is to have two boundaries, one associated with each of the operators. And then because here we are focusing on the connected contribution, we look for some connected contribution where you have a wormhole connecting the two boundaries, and then we are free to connect these dots in various ways. Now, a simplification where they assumed in their paper is that for operator O with very heavy dimension delta much greater than 1, the crossings of these lines are suppressed. So you simply have all the diagrams where these red dots are crossed by lines that do not cross each other. Now, a very interesting properties of this particular BPS configuration is that usually when you have such gravity configurations, all these lines will give different answers because for example, the distance between these 2 points might be closer, but the difference between these 2 points might be much longer. But what happens in this funny situation is that because of rarely there is this infinite Euclidean evolution between any 2 points. If you think about it more carefully, all these lines actually give exactly the same weight. So in this BPS limit, they all approach the same constant. Okay, so that makes the calculation really simple. You just, because all the lines give the same weight, the answer that you get is basically just proportional to the ways that you can perform these contractions, that you can connect these dots. Now, they then immediately recognize that the diagrammatic rule here, the way that you connect these dots, is in fact equivalent to doing weak contractions of a Gaussian random matrix H. So let's imagine that now I have some Gaussian random matrix H. I just want to compute this connected correlator by doing weak contractions. I will also try to connect operators in the 2 traces in these different ways. And the planar contractions are exactly the same ones as we are doing here. So this is a roundabout way of saying that in the end, you realize that the diagrammatic rule in this BPS context is equivalent to doing weak contraction using a Gaussian random matrix. And they think about computing the spectral form factor as first Taylor expanding it. And so then you're already computing the relevant computation is indeed this kind of correlators. And from that, they justify that in the end, the ramp of these projective operators should really behave the same as a Gaussian unitary random matrix. So one will find a linear ramp which starts at order 1 time. You have order 1 Thouless time. Okay. Okay, so this is just some review of the gravity story. So in the next part of the talk, I will tell you what we did in the D1, D5 CFT. And if I have more time, I'll tell you a little bit about what we did in the n equals 4 super Mills theory. So here, the idea is that we tested the LMRS computation, this projected, and then look at the spectrum calculation using a special subset of the half BPS states in D1, D5, and a special choice of operator. So in the D1, D5 case, we we were not working extremely hard. We did more work in the n equals 4 case. So here we just make the choice such that we don't need to compute the matrix elements ourselves, because the matrix elements are readily computed in this very nice paper by these authors in 2015. And so we can simply use their results and proceed to analyze the special properties of this projected operator. Okay. Now, for simplicity, I will just phrase what we did using language of the symmetric product orbifold. But since the half BPS states are protected as well as the relevant matrix elements computed by these authors, the discussion have some extension also to the strong coupling limit. And I think it would be an interesting question to ask whether one can understand it using the language of gravity. But I don't have useful things to say about that now. Good. So let me briefly review what the setup is. For more background, well, most of you know this theory much better than I do, but for more background, I refer you to this paper. Now the D1, D5 CFT has R symmetry group SU2 left times SU2 right. In the Ramon sector, where we're looking at we're here now looking at the ground state, for each strand of the symmetric product orbifold, you have 16 ground states. What we did is to simply select a particular state with R charge J left equals to J right equals to 1/2. So that in the literature is usually denoted by the plus state or sometimes plus dot state. I will not use this notation later anymore. Now, in the NS sector, this corresponds to half BPS states with the scaling dimension H equals to the R charge J, which is equal to K plus 1/2, where K is the length of the strand. So you can have strand with different lengths. Now, after these restrictions, so we consider this particular state in each strand, then the half BPS subspace is simply labeled by the strand structure. So as you all know, that the states are simply given by conjugacy class of Sn, and they are labeled by different cycle structures. So they correspond to different division of n, and the number of states is equal to the partition number of n. Now, the operators that we choose, which follow this paper, are these BPS twist operators. So we consider two operators, and we eventually take a sum of these two, and there's a chiral part of the operator, which using their notation is denoted by sigma 2 plus plus, which is a BPS twist operator that has h equals to j and h bar equals to j bar equals to 1/2. And then there's an anti-chiral part of the operator, which has negative j left and j right, equals to negative 1/2. Now, roughly speaking, I would write down a more precise formula on the next slides. But roughly speaking, when you act these sigma 2 plus plus on the half BPS states, what happens is that it could split these half BPS states with length L1 plus L2 into two strands, one with L1 and one with L2. So on the right-hand side, you have a term like this, among other things. So you have you can split it apart, but you can also use sigma 2 minus minus to join two strands. So you can start with a strand with L1 and a strand with L2, and these other operators join them. Now, here, let me just show you the final formulas using the results they wrote down. So basically, what this formula is the form of these operators once I project them into the subspace of these particular half BPS states that we are considering. So let's see. Let's unpack this formula a little bit. So the sigma 2 hat, the projected operator minus minus, annihilates two strands. So these alphas are some annihilation operator that one can define. It annihilates two strands of L1, L2 and creates a strand with L1 plus L2. And there are some other factors that just keep track of the group theory factors, and as well as some overall coefficient C, which is equal to L1 plus L2 over 2L1 or L2. So it's a number that is smaller than 1. And similarly, we have this other operator which annihilates a strand with L1 plus L2 and then creates two strands, one with L1 and one with L2. And the operator that we study is a linear combination of the two, which is the sum of these two operators. Okay, so this is the setup. So at this point now, the goal is just to analyze what the spectrum of this operator look like. And that turns out, to analyze the spectrum of this operator turns out to be a very interesting problem. And there are, let me talk about various different aspects of it. So what can we say about this operator? Now, the first thing connecting to what I said earlier is that if you actually look at this operator, it actually has this banded structure. So the idea is that we can organize states based on the features of these half BPS states based on the number of cycles involved in the half BPS states. So the cycles ranging from 1 to n. And in this plot, so let me explain this plot. So in this plot, the left corner corresponds to cycles with only, I think it's only a single cycle, while the rightmost right bottom corner corresponds to cycles where you have n individual cycles. Okay, so you order states in that way. And what you see from this operator is that because every time it only joins two strands or splits one strand into two, it at most, well, it only changes the cycle number by one or by +1 or -1. So that means if I order the states in this way, the operator would only couple nearest blocks. So the states are all organizing in blocks, and we only have non-zero matrix elements in nearby blocks. Now, Now, following this banded matrix idea, we would like to have a particular quantity that we would like to look at is how big is the width compared to the total size of the matrix, okay? So for that, let me define this quantity T of K and N. So the idea is that I can divide the partition of N into a sum over K, where this T quantity is defined as number of ways that I can divide N into K parts. So for example, T1 comma N is equal to 1, and Tn comma 1 N is also equal to 1, but it becomes larger in the middle. And that this T basically corresponds to the size of these individual blocks, right? So that controls the maximum of T, controls the maximum width of this band. So here I'm here, this plot is taken with a particular value of N, which is equal to 30. So here the total size of the matrix is 5,600 or so, but then this width is basically a few hundred. Now it was actually studied by mathematicians, by Edosh and others, Lerner, and that the maximum of this T maximum over K of this ratio can actually be calculated exactly, and that is equal, the large N scaling can be calculated, and that is given by some order 1 number, this number written there, divided by square root of N. Okay. Now, was there a question? No.
This calculation was done in random matrix theory, right? It was not done in the DOD5.
Yes. Yes. No. Here is just a math. This part is just a math result about the partition, so it doesn't have to do with the matrix. But here, what I'm gonna say, yes, is in the random matrix, if the operator is a banded random matrix, that would suggest that the Thouless time is long. Thouless time is of order N. So that answers your question?
Yes, good.
Yes. So the idea is that if this matrix is random within this band, okay, and I just have random matrix elements, then we can use this random banded matrix result to put an estimate for the Thouless time, which we suggest is at least of order N. But of course, the actual operator is not random, and it is in fact very sparse. It's if you look at how many matrix elements are there non-zero in this band, it's very small. So these arguments, strictly speaking, do not apply, but one might expect that by choosing a more regular matrix compared to a random matrix, that only increases the Thouless time. This is not a rigorous argument, but we will see that this estimate of order N matches with some other estimates that I will talk about now. Now, the second connection, point I want to make about this operator is a very curious and interesting connection to a different math problem called card shuffling. So remarkably, a closely related operator has already been studied in the math literature. So that operator is simply an operator where you replace this coefficient, which is a smaller than 1 coefficient, by 1. So I just replace all these C's by 1. Then this operator actually has been studied in the math literature. And I don't want to go into too much detail, but here I just show you the original paper that studied this operator, which is titled Generating a Random Permutation with Random Transposition. So the rough idea is the following. So you can think of each cycle structure as corresponding to a particular ways of shuffling the cards. For example, if I have a deck of cards from 1 to 52, then if I don't shuffle the card at all, I just have 1, 2, 3, 4 to 52. That ordering corresponds to a permutation that has n cycles, right? 1 to 1, 2 to 2, 3 to 3, etc. Now, starting from that, mathematicians were curious about the question of if I apply some operation, some particular shuffling scheme, how long do I need to shuffle how many times do I need to shuffle the deck such that the final result looks random? So that is a classic problem. And here, the particular way of shuffling the card corresponding to this operator is a random transposition, which means that at each step, I just pick 2 cards at random out of the 52, and then I swap them. So this obviously is a very inefficient way of shuffling the cards. And these mathematicians, by studying this modified operator, were able to understand how many transpositions you need to eventually reach random. Okay, so there again, the picture is kind of again, it's similar to this banded matrix. It's kind of a diffusion motion on this different on this Cayley graph of Sn, and the idea is that you need to have times n log n many transpositions. So it's some large number for the final deck to look random. Now this is just some curious aside, but as a side product, they have studied the spectrum of this operator exactly. So the idea is that if I modify these C's to be 1, I can actually find the eigenvalues precisely, and the eigenvalues are given by characters of this tau corresponds to transposition. So the character of the transposition group element in the representation R divided by the dimension of representation R, where R is is one of the irrep of Sn. So you just have these very nice formulas for the eigenvalues. And if you plot them, you can plot them for just compute these and look at some moderate value of n. You see that the spectrum has very large degeneracies, in fact, and has no chaos. So if you plot a histogram of eigenvalues, there are these peaks. So in fact, many of these numbers are the same, and they have these peaks, and there's no chaos in this modified problem. Of course, again, because here we're again changing the problem. So this modified problem, this does not immediately imply anything precise for our actual operators, where we changed the C coefficients to be the actual value. But one intuition that we think do carry over is this notion of diffusion time, that it takes a long time for this operator for local excitation to spread across the entire system. So from these, one will give an estimate of the Thouless time that is, again, order n up to some logarithmic factors. Now let's just look at the actual operator now, instead of looking at some closely related problem. What if you actually diagonalize this operator numerically? What does the actual spectrum look like? So it has a very curious spectrum. So the spectrum kind of resembles this modified operator where you have these huge peaks, but all the degeneracies are now broken. You have many peaks, and each peak are spread a little bit. So if I zoom in into some smaller window, you see you have these individual clusters of eigenvalues, and they don't touch. There's some finite gap that separates them in the middle. So it's some very curious spectrum, and I have to admit we don't have a very good understanding of why the spectrum is like this, other than the connection to this card shuffling problem. Now,
sorry, in the card shuffling problem, essentially these are just delta functions, right? This distribution.
Yes, there is just delta functions.
So essentially what's spreading them is the fact that this coefficient C, L1, L2 is going to be different, and that's enough to spread them.
Yeah, like small change of C can just completely remove these degeneracies, just lift them.
But can you make a large enough C to merge them into each other, or people haven't done that? I mean, if you just play some, you have a function C, you can just play with it. If you play with it, can you make these things merge into each other much more and give you the semblance of a random, of a chaotic system? If you just play with the C.
We have. I will talk about that later. Yes.
Thanks.
Okay. Now, within each peak, what we found very well, I guess we didn't expect it at the beginning, but if you really look at within each peak, if you look at nearest neighbor spacing, you find perfect chaotic signature. You find Wigner surmise. Here is a histogram of level spacing between nearest neighbors, and that is a beautiful Wigner surmise. Now we have not been able to observe a clear linear ramp for this operator numerically, which partly might be because of the ramp time is late. We expect it to scale as n. So for this moderate range of n, that means that the time between the ramp and the plateau is relatively short. So that might be an explanation why we were not able to find the ramp very clearly numerically. Now, as a first pass, another comment about this operator is that one might view that each cluster as coming from, well, as a first pass, you might think each cluster is an individual random matrix. Of course, there's a question of even within each cluster, how chaotic it is. But let's say that within each cluster is just a perfect random matrix, and different clusters are uncorrelated. They correspond to independent random matrices. Then from these, you can also give some estimate weak bound on the Thouless time, because you see now you have many clusters, and only within each clusters you expect the random matrix statistics. So that would provide some further bound on the Thouless time. But this is again some weak bound, which is not very satisfying.
Can you argue that the clusters are identified by something? I don't know. Do they have different angular momenta? Because, for example, the states in the D-5 system, they have a huge range of spins. They have an angular momentum going all the way from N1 N5 to 0. Can you argue that the clusters are just clustering because of some angular momentum, not allowing them to mix too much? Because
we tried. So I think your question is like, what if I look at the eigenvectors in each cluster? Do they like concentrate at some particular part in this matrix, right? That's kind of what you're asking. But we looked at it. It seems kind of spread out. So we didn't find a clear pattern. It might be we didn't try hard enough, but preliminarily we didn't really see a pattern.
Okay, thanks.
Good. Now, as Joseph was suggesting, so here we actually have a lot of flexibility, so we can kind of play with these Cs. Now, to gain some more insight, we considered a random C model. So we just choose the C to be random. Okay, we just random. Well, I think we actually random from 0 to 1, so some random number between 0 and 1. Now, the benefit of that is that we kind of enlarged our ensemble of operators. Then we have an ensemble of operators which we can then start to get some good statistics, right? We can do some average over the ensemble and get some good statistics. So here, let me show you. This is a plot of what the spectral form factor look like. It's a spectral form factor. So in the log plot, so it has an initial decay. It does something. Or in the log plot, it looks pretty quickly. It goes to linear ramp, but it's actually a very long time because here t is 100 or so. So it does something before the ramp, and then it transits into the ramp. And in this case, it's actually GOE. So here there is some smoother transition to the plateau at late time. Now, using this kind of graph, you can then estimate what the Thouless time is. So the idea is that you draw a linear line across the ramp and see what is the time where the green curve, starts to deviate from the linear line. You can set some criteria and say deviates by 10%, deviates by 20%. So this blue dot is 10%, red dot is 20%. So here, I think this is a good indication of that the Thouless time indeed grows with n. And well, numerically, it's hard to say for sure it's linearly, but at least it looks kind of linear. So here I'm plotting the Thouless time defined in this way by looking at when it deviates from the linear curve as a function of n. So I have two different curves, one for 10% deviation, the other for 20% deviation. You see the trend that it does scale as n. Okay. So, well, in the paper we discuss in a lot more detail, but the upshot is that combining all these various different evidences from different fronts, we give a conservative estimate for the Thouless time to be at least of order n. I find interesting here we find that the half BPS states are chaotic, but based on this criterion of weak versus strong chaos, we find that it is weakly chaotic. Okay, now since I'm going out of time, let me just skip over the n equals 4 CPM Mills case. Basically, what we did is that we looked at the half BPS sector where the story is in fact very similar in spirit to the D1, D5 half BPS case, where we'll also find this banded structure, and we can use that to give some estimation of the Thouless time. But there, we also studied some operators where we can actually solve for the spectrum exactly. You can find our paper for more detail. And for the quarter BPS sector, I think it's a very interesting problem and it deserves more attention because it's a case where one needs to study the lifting problem. So in both of these half BPS cases, the states are protected. So we don't need to put any effort into finding what the BPS states are. But once you, let's say in the n equals 4 CPM Mills case, once you go to the quarter BPS case, you need to, most of the quarter BPS states in the free theory get lifted once you go to the interacting theory. So there is a non-trivial lifting problem that you can study. And that lifting problem has many interesting features. So if you are interested, I would be happy to talk about it afterwards, or you can check out our paper. But the upshot is even though you have this non-trivial lifting problem, numerically it seems that the quarter BPS states at one loop still look like weak chaos. They don't exhibit the strong chaos that we expect for supersymmetric black holes, which from the bulk it's clear that they are different from macroscopic black holes. Okay, so let me skip over this part of n equals 4 CPM Mills discussion. And just
is there any dependence of these results on which class of half BPS states you consider?
That's a good question. So in the you are asking this in the D1, D5 context?
Yes. So I'm wondering if I look at some states that have extremely long cycles, so they'll look very close to an extremal black hole, whether the results qualitatively depend on the length of the longest cycle, say, in the half BPS state you're considering.
Right. So I guess at least if I choose in the half BPS case, if you fix the cycle length, then there are less states, right? So there are not many states to study, but yes, I think if you restrict to some range of the cycle length, then the structure of this banded matrix will certainly change. And I think one can try to study how the spectrum of this projective operator changes as well. We haven't done that analysis. I think the related question would be much more important in the quarter BPS case, which I guess I'm going to comment a little bit about now. So the idea is so we can ask what happens in the generic 3-charge case. We expect the strong chaos for the generic 3-charge black holes. So how does that happen from the field theory point of view? So one comment is that, first of all, even in the free theory, the distribution of states will be modified because of all these fractionated modes. So I heard from Chen, and maybe he can talk a little bit more later, that he and collaborators have been studying this problem where taking into account this fractionated mode, how are this picture that I have here like rescaled? Maybe some blocks becomes larger and some blocks become smaller. So that certainly would already have some implication on the projective operator, even in the free theory. But I think more importantly, similar to the n equals 4 supreme Mills case, to really understand this problem, it's important to understand this non-trivial lifting problem, which of course many of you know much better than I do. So the idea is that many states get lifted once you try to go away from the orbital point. Now, I think we expect the distribution of BPS states to change dramatically. I think Hao Yu, he will be giving a talk next week on this kind of lifting problems in D1, D5, and he might have more comments on these. So I think I don't have too much concrete things to say, but I think understanding this lifting problem better is essential in trying to understand questions about chaos and this LMRS calculation. And even though I didn't touch on this at all in this talk, but there is I think, very interesting connection to this idea of fortuity and the Schwarzian theory, which would shed some light here. Like in this generic 3-charge case, we should have both monotone states and fortuitous states. Can we really see, is there any reason that the projection of a simple operator into the fortuitous states would behave qualitatively different from projecting it into the monotone states? So that would be a concrete question that I think is answerable in the near future. Okay, let me end by this is my last slide. Just talk about a subtlety that we're currently investigating. So far in my talk, I'm always focusing on these very simple solutions, like solutions with just stuff in the middle of the bulk, either black holes or some Looney-Mathur geometry, some fastball geometry in the bulk, in the center of the bulk. But one problem about the Thouless time is that in theories with ADS localities, or the ADS space is big, we can have a lot of stuff that is not in the center of the bulk, but like kind of far away from the black hole or from the object, which could, in principle, in some sense, contaminate the signal of the Thouless time. So to be clear of what I mean, for example, if you have a black hole, and I mentioned earlier that the Thouless time is related to the long-lived modes on the background. So if I have some orbit, some graviton that is orbiting around the black hole very, very far away, it could have a very, very long lifetime. So that could kind of obscure what the Thouless time really is. Now, this becomes relevant for the BPS context because recently there have been very interesting discussion by Su Kim, Shiraz, Binwala, and collaborators, where they proposed such BPS configurations where you have stuff far away from the black hole. So what they call these BPS great galaxies, or these dual dress black holes, which are black holes enclosed by some deep ring, etc. So I think it's a very interesting question of what the spectral form factor would look like for this kind of BPS configurations, and whether we can distinguish them from just some solution without a horizon, but that does not have stuff far away from the object. Now we're currently investigating the behavior of LMRS computation in these cases. I think our rough picture is that these effects lead to modifications to the linear ramp at early time, but there is still some sharp signatures that can distinguish like this kind of behavior from the banded matrix that I discussed earlier. But hopefully we will have more to say on this question. With that, I'd like to thank you for your attention.
Thanks. Thank you. Thanks a lot. Thanks. So I have a question actually about this BPS gray galaxies. So long time ago, we constructed this solution with Jan de Boer and Masaki Shigemori for the D1D5 system. So in the D1D5 system, for example, you can take a black hole and you can put a super tube around, or you can put some other garbage around the black hole. I mean, this is something which, and for example, you can argue that in the D1D5 system, when the angular momentum is very large, Then the supertubes dominate. The black hole with the supertube has more entropy than the single black hole, and so on. So this is about
I see.
almost 15 years ago. But the problem is most of these solutions which involve supertubes, they can be built in string theory, and in 10 dimensions. But because they have angular momentum, the moment you want to go to some Euclidean calculation, to the Euclidean calculation on them, they don't have any Euclidean version, because the Euclidean solution is imaginary. The metric is imaginary. So when you have garbage around the black hole, usually that garbage spins, and it's very hard to make a Euclidean solution corresponding to that. So I don't know how can one investigate these things? I don't know. It's just my lack of knowledge. Nobody investigated our things long time ago. Was that they are just not. First of all, they don't fit into any 3D gravity. They are like intrinsically 6D solutions. But moreover, they don't have a Euclidean version. And I think the black rings are. There's a similar example of the black ring. So you can take a black ring, the black hole spins so much, at some point can become a black ring. So there's a way. I mean, these things were discussed a long time ago in the context of the D1D5 system, but I don't think it's possible to do any Euclidean calculation on them, at least on the ones I know. So I'm just wondering, how can we get, for these gray galaxies, how can we get Euclidean calculation?
First of all, thanks for telling me about those. I should have included here. I just didn't think about it. That's a good point, because of this rotation does not have a nice Euclidean continuation.
Well, it's just complex.
You will get some complex things.
People looked at this. We had talks about this last year from people like Samir Murthy, and that you just have to. That was in the context of finite temperature, but allowing for rotation. So, there's a suitable notion of analytic continuation that might be appropriate for addressing these sorts of issues.
But when you have lots of fields, also this Euclidean calculation becomes, I guess, harder and harder. I mean, if you don't, I mean, if you just have a black hole and you spin it, great, you can describe it in 3D gravity. Just forget a BTC black hole. But most of these configurations, they don't have any sphere isometries. So, for example, the black rings, you cannot bring them in as an ADS3 solution, as a solution in ADS3. So,
I think, I don't know in general, but here there are some cases where you still preserve this spherical symmetry and have nice Euclidean continuation. They still address black holes, so maybe that would be simpler to study. These are black holes that just have some static deep rings surrounding them, so that you can continue to Euclidean signature.
okay.
But I think probably I think there should be some way to phrase this question just purely in the Lorentzian language, like what is the effect of this stuff far away from the black hole on this projective operator? One should be able to understand that without resorting to the Euclidean method. We are still thinking about it.
More questions from people on Zoom. We have many people. Go ahead, Ishan. Yoav, go ahead.
Is it obvious that the Tholos time is different away from the free point of the D1D5 CFT?
Well, we only talked about the half BPS case where these things are protected. So there, the answer is yes, but no, in general, no. In general, I expect it to be very different in the free theory versus the interacting theory. For example, in this three-charge case, I think one should be able to see qualitative difference in the free orbital point versus the first order perturbation away from that.
I have a question.
Yes.
Can I ask about the model with the random coefficients? Could you go back to something about that?
Let me just find that. Yes.
Right. So you're the CL1L2. So firstly, as you know, and as you summarize, this is an output of a calculation in the orbifold point. And as you know, that was something I did with Samir Mathur and Sean Hampton and Zach Carson. And so that's a calculation which we don't have the right to change that at will.
Yes.
And it has the property that, as Emil was asking about, for large L1 and L2, if we just think of them to be comparable in size, if we take them to be, say, of order square root of n, where there are many states, then the C goes smaller as we increase L1 and L2. So it'll be like 1 divided by square root of n. So I was wondering, when you made the random model, which is, of course, an interesting thing to do, did you account for this property? Like, did you take into account some L1, L2 dependence in how you defined your random variables? Did they have a mean value that would agree with CL1, L2, or did you just take them to be, unit variance over with no dependence on L1 or L2?
Yeah, well, I think we just took it to be completely random, but that's a really good point, to maybe have some like profile that is kind of decaying when L is large, and then I'll add some randomness on that.
Right. Yeah, it might be a little bit closer to what the orbifold CFT actually gives you.
Right. That might be closer to the actual problem. That's a very good suggestion. Thanks. And yeah, also, sorry, I didn't put to reference here because this was I made the slides last night.
No worries.
Late.
I'm a little confused about what I'm supposed to conclude from this sort of a calculation. So, because one is studying supergravity operators, which, okay, it's some single trace thing, but in a theory where you've essentially turned off gravity because you've turned off the twist 2 perturbation. And so if I'm really going to model something which is appropriate to the gravity regime of the conformal field theory, I should turn on that twist 2 operator by a large amount. And then it starts scrambling up all of this cycle length data like crazy, right? Because it starts, that twist 2 operator, it's sort of like, the thing you were banking on, which is that it takes you lots of transpositions in order to rewire the cycles. Well, that's kind of automatic once you're in the supergravity regime because you've turned on this twist 2 perturbation by an amount of order 1. So I'm a little confused as to what I'm supposed to conclude from this sort of calculation that's relevant to the gravity regime.
Well, correct me if I'm wrong, but I thought at least in this half BPS context, this cycle structure still persists in the strong coupling regime in the gravity.
It labels the BPS states, but if I want to ask, what near BPS things am I communicating with, and how far apart are they in this basis? I'm not so sure that there isn't an order of limits issue. What the near BPS state space is, what it looks like in this basis. And do I move very far in the cycle structure in order to access those states?
Right. Perhaps, I guess maybe your question would be even sharper if like the operator that I projected is some non-BPS operator, then that could, once you turn on the coupling, that could have some corrections to away from the free point. So
yeah, I'm just confused about the naive version of turning on gravity is to turn on the transposition operator, and so and yet somehow when we go do calculations, for instance, in these worldsheet theories that describe supertubes, we can still make a match to what the BPS operators are doing to these things. So I don't have an answer to this question. It's something that has puzzled me for a long time.
right. Yeah, I think, well, I don't have a very good answer, but I think maybe here is special because maybe as you go away from the free orbital point, as you kind of scramble these bases of different structures, you are also kind of transforming this operator that we're using to probe the BPS states. So in this case, all these matrix elements are protected quantities, so they don't really see this effect of the twist two operators scrambling the cycle that you were talking about. But in the
I can comment, Yiming, which
Yes,
you should
please.
correct me if I'm wrong, but the way I was understanding what you told us is that this is like a perturbative toy version of what Emil is talking about, namely that you're sort of turning on this twist two at first order in perturbation theory.
Mhm.
It's not exactly the deformation operator because you don't have the
Yeah,
supercharges, but
yes.
it's a very closely related thing because you just act with two supercharges on your sigma 2 plus plus or minus
Yes.
minus, you get the operator Emil is talking about. And so you're just switching that on a first order perturbatively away from the orbifold point as a first step, a toy model of what Emil is describing of turning it on non-perturbatively. And you're seeing what you get from that at first order. But is that a correct summary of what you're attempting here?
Well, that's not how I think about this calculation, but of course, well, if you actually use the twist two operator that you deform the symmetric polar orbital, the matrix elements will actually be zero, right?
Sure.
Due to these super partners that you were talking about.
Sure.
So
Yeah.
that's the statement that these half BPS states are protected.
Exactly. So you're somehow doing a toy version, which so you want something non-trivial at first order. And
I'm not really thinking about these operators as trying to deform the orbital theory away from the free point. So in the free theory, I just think of this as a way of doing this LMRS calculation. I choose some simple operator. I look at whether it's matrix elements, what in the how PPS states are, and what the spectrum look like. And here, because of this supersymmetric magic, the same calculation it can also be done as strong coupling if you choose the half BPS states as strong coupling and the corresponding operator as strong coupling, and then the matrix elements will be the same. So that, in fact, I think in that paper I cited they matched the 1-point function of this operator between the free theory and the strong coupling gravity calculation. So I think it's just well, my feeling is this half BPS case, we just don't see the coupling dependence. To really maybe probe the question of the coupling dependence, we should choose some operator that is non-BPS, or we can go to more complicated situations where the BPS states themselves also gets deformed, their wave function changes as you go to strong coupling. So I think this we didn't do in the D1D5 case, but we did some of this in the Anchorage 4 case.
okay, thanks.
Well, I mean, the 1-point function is not a very strong test because, as you say, it's completely controlled by BPS properties.
Mhm.
But you're making a somewhat stronger statement, which is that arbitrary correlation functions of the LMRS sort have some sort of universal behavior, right? And so, and once I start looking at multi-point simple operator correlators, then the intermediate states are non-BPS and are not protected. So I think those calculations would be a much more stringent test of these sorts of ideas.
I completely agree. So we didn't do that in the D1D5 case. In the Anchorage 4 Super Mills case, we did consider using some non-BPS operator. But of course, our discussion there is still limited in the weak coupling limit. But we can perturb the theory away from the free theory. Now, I think even okay. So the concrete calculation might be hard, but I think the intuition that these half BPS states are structured, I think that persists in the strong coupling limit, that they have this you can organize them by the cycle structure. So they have some building structure within that. I think that feature is universal and also applies to strong coupling. And I don't think that even by acting with just let's say product of a few simple supergravity operators, you will be able to change the cycle structure too much. But I might be wrong on that. That's my intuition.
You all go ahead.
What is the relationship between the LMRS criterion and the out-of-time order diagnosis of chaos?
Well, I mean, the out-of-time order thing, as far as I understand, only applies for the non-BPS contest. So I don't know how to directly compare them. Can you maybe elaborate more on your question?
Well, I don't have an idea.
Well, I mean, the out-of-time order thing usually is for non-BPS where you have a time evolution, but you can of course compare out-of-time order thing with the analog of LMRS in the non-BPS setting, which is maybe the statement of ETH. And I think that is a very interesting question. How does ETH relate to the chaos of out-of-time order correlator? I think that, yeah, well, the short answer is I don't know. I can, yeah, I don't think I have too precise comments to make on that. But I think it's an interesting question.
So I had a question about the bulk version of this calculation. So for example,
Yes.
if two charge, so okay, you compute this expectation value. So you take one heavy operator, you take another heavy one from the perspective of the bulk, and you have a light one which is squeezed between them. You do all these calculations that we're coupling, and then you go in the bulk. And I was just wondering if there's a way to see this rigidity in the spectrum, the fact that one object doesn't want to go into another one. I was wondering if bulk calculation to be done. And I remember a long time ago, Samir was saying that he did some calculation about the super tube, and he was smashing the super tube with some graviton, and the super tube was quite rigid. But I'm just there's a way to relate these things. I don't know if Samir is online and can comment on those. I mean, I don't know if there's a way to recover your calculation by just doing a gravity calculation in the bulk. So, for example, again, you have some. So, if you look at one state, it corresponds in the bulk to some super tube of some shape, and then you hit it with an operator, and then you have it. You make it into a super tube of a different shape, and you absorb the operator you throw in. So that's something which, and I remember, I mean, I think 2 years ago, I was saying, oh, and this will be random. You put some energy on the super tube, it will go all over the place, it will go explore the full space. And Samir was saying, no. Super tubes are very rigid. When you ping them, they're going to be. I mean, you don't excite the states nearby some shape. So I don't know, Samir, if you want to say a few things, if there's a link, if there's a way to link this with your calculation.
So I can just mention what the calculation was, and then maybe just to clarify the question further, and then maybe Yiming can say something about it. So the calculation was that there are two different limits we found. If you go to the weakly coupled gravity where you have a super tube in flat space, then if you give the super tube a little kick, there are super tube, if it is not maximally rotating, of course, for the same angular momentum, there are many possible shapes. And so you could ask if the super tube will actually keep moving among all those shapes in some kind of a trajectory, just like a motion on moduli space. And there you find very easily that the answer is no. It's not like motion on moduli space. All those super tubes actually have the same charge and energy and angular momentum, but it's like being on a plane which has all points at the same potential. And you might think if you kick a particle, it will just keep drifting like on a moduli space. Except that's not the case. What you really have is like a particle on a plane in a magnetic field. So you give it a little kick, it makes a little circle, comes right back. So if you take a super tube, you give it a little kick, it goes a little bit around itself, but it doesn't go very far. Now, when you increase the gravity to make it a deep throat and you have a cap at the bottom, then those modes get completely frozen. Even those small vibrations of that super tube, they become heavier than something else. And the something else is the vibrations of this throat. So the throat which are now developed, which is long, those modes are actually lighter than the actual modes of the super tube. And you can see where that transition comes in terms of fractionation of brains and so on. The order of magnitude can be inferred from that. So that was just to clarify what Joseph was asking. But yeah, that's an excellent question. And I would love to hear what Yiming Chen was saying about it.
Yeah, thanks for telling me that. That sounds fascinating. I think this, what you just said, that by perturbing the super tube a little bit doesn't change it that much. It has some rigidity. Sounds exactly like this banded feature that we saw in this free theory calculation. So I think it would be very interesting to relate the two maybe more precisely. But then, as you said, the throw gets longer and longer, and the soft mode becomes the vibration of the throw. That sounds to me maybe the key to understand how the eventually the strong chaos gets developed. Really, like the soft modes become different. Yeah, I think that would be very interesting to understand.
Yeah, that may become clearer after my talk tomorrow.
Oh,
I will address precisely this issue. And if I don't, ask me a question.
that's great. Thank you.
Coming back to your question, coming back to your graph about this nice diagonal line with bumps on it. If you can go back to it. So there you cannot identify that, in the bump. No, the one before, the one you have.
The which bump?
The one with bumps, the one with diagonal. Go on the next page.
Next slide.
The one with the matrix, the one with the matrix with diagonal bumps.
This
one. Yes. So you cannot identify, for example, in this region, you cannot say, oh, those are eigenvalues corresponding to some supertubes of some charge or of some angular momentum. You cannot identify in any way, in one of the bumps. If you just look in one of the bumps here.
Sorry.
Look at this particular bump when you have those are all eigenvalues which go into each other. So I mean those are all guys which talk to each other. The guys inside one bump.
I'm not sure I entirely understood the question. So here I'm ordering, the matrix is ordered by different ways to divide n into k parts. So I would say that within each blocks I have some particular configuration of the supertube. Can you ask the question again?
Yes. No, this is the whole question. So if you look, for example, again at one particular configuration here, so you're saying this corresponds to one type of supertube, let's say of dipole charge, I don't know, corresponding to the number here, which is wrapped around, so a supertube wrapped around, I don't know, 5 times, and which has charge 6, so it will have like some radius 36 or something, so it's some.
Yeah. You should be able to say that. Yeah.
But in a sense, this is what Samir is saying. Samir is saying, I have a supertube which is wrapped k times. So this is the supertube which you have here, and then if you bump it, if you hit it, it will go into nearby objects. So this matrix will just be localized here. It will not take you here.
Yeah. I think it's exactly related, but yeah, I think it would be better to understand more quantitatively.
Then I think it's possible to get, so the fact that you get smaller and smaller bumps here, the fact that you get, as you approach this limit, you get smaller and smaller bumps. In this limit, is this the limit when the throat becomes deeper, or is your bigger dipole charge longer throat in this direction?
I need to remember how I ordered this graph.
Or the other way?
It gets smaller on both ends, so yes.
Oh. The size, so there's the size of the supertube, or there's an angular momentum, for example, of the supertube. If you label the angular momentum,
the angular momentum, I think, should be largest on this side.
Okay, so the guys here in the corner, they're the small guys. They're the tiny supertubes which become deeper and deeper I see. Because it may be a way to just relate Samir's calculation about with Landau levels and the dependence of the dependence of the rigidity on how close you are to the deep throat. I mean, the fact that his mode becomes more and more massive, more and more rigid. There may be a way to relate it with the thickness of your. You have a thickness, has some thickness. This guy has some thickness, and this thickness varies. I mean, here, for example, you can see that the thickness is becoming smaller and smaller and smaller as you go down. So maybe there's a way to do a calculation to relate this thickness of yours with the amount with Samir's calculation. I don't know. I'm just saying.
Yeah. That sounds possible. Like if there's a way of relating the width to the depth of the throat somehow.
It looks like it is the case, right? Because somehow, so the way you organize the states is that on the left you have put all of your you have put the longest strand, and on the right it's about the strand. I mean, sorry, the maximally untwisted sector, right? So it's just like the single strand. So if you assume that the single strands they are not going to produce a deep throat, then in the end this is so then your deep throat microstates are going to be on the left, on the top right corner.
Yeah, I might have set it in reverse. It might be here. Yes.
And so I guess that the idea is that the more you go to the right, the shallower is the throat, and the interpretation is that in the end, what Samir is saying is that if you're deep, the throat is deep enough, so that you start like on the left top corner, then you stay there. Can I understand that way?
Right. So you kind of zooming into that part of the matrix and
Yeah, I think so. That somehow that also if you add the third charge, then actually you have much more states in the k equals to 1 sector and also k equals to 2, right? And I guess that's I don't know if you agree, but I would expect that the k equals to 1 sector is when you really reach like 1/n1/5 as the fractionation. If you're a little bit more in the middle, then you would not like have 1/n1/5 fractionation. You would have less fractionation.
Yes.
And so something like that.
Yeah. So once you go to the 3 charge case, the left upper corner would get blow up, like you have a lot more states. I think that's the right intuition. Yes.
Because the point is, if we can do this calculation, so let's suppose there's a way to calculate this thickness in the bulk. Then we can do a very simple example of a 3-charge microstate. Because instead of doing so, you can do 3-charge microstate, okay, using bubbling geometries or superstrata. That's pain. But there's a simple way which we did with Nick a long time ago. We just took some bubbling geometry which has bubbles, and those bubbles are pretty rigid, so I'm not going to excite them. I just have some bubbles sitting here, and then on top of the bubbles, I'll just add a super tube. So you can actually take a super tube and you can add it right here on top of, not like that. You'll add it, sorry, let me go back in the picture, back like that. You'll add it like this on top of the bubble. So this is a round super tube, what I'm drawing here in red. And this solution, for example, can go down, you can have a very long throat, and you can do some calculation. Then you can just take the super tube, but again, it will be a super tube living deep down the valley, and you can just do some calculation. And you can calculate how much this width will be when you go in the long throat region. So then you can take your calculation and you can just extend it for free to the 3-charge states. Again, it will be some particular 3-charge states. The CFT dual is not known, and so on and so forth. But it will give you, when you have the typical 3-charge states which you expect to have a long throat, it will allow to tell you whether this, what this thickness will be for this particular 3-charge states. If there's a way to get Samir's calculation to link with yours. Again, Samir's calculation is done in the bulk using super tubes. If I just put super tubes deep down this long throat, I can do the calculation there, and then if I do the calculation there, I'll be able to get this thickness. That's some way to get this thing from the bulk.
Sorry, Joseph, I did not understand how you can relate the thickness to the.
So what Samir was saying,
Samir's calculation.
Samir was saying is the following. You take a super tube of dipole charge, of some dipole charge, and then you hit it. Naively, you say, there's a moduli space, any function is a good function, so therefore there's a moduli space of dimension n1 and 5. The super tube has n1 and 5 directions where it can go, so it will just spread uniformly in the moduli space very happily. But Samir did a calculation, and if I understand him correctly, what he's saying is that no, the moment there's a moduli space indeed of size, so there's a huge moduli space of dimension n1 and 5, so we're talking a super mega big moduli space. So naively, when you have a huge moduli space, you put some excitation, and you expect it to spread uniformly all over the moduli space. But in the supertube example, because there's some magnetic fields, this guy spreads in the moduli space a tiny bit and comes back to itself. So the supertube which you have here will move a tiny bit and then come back to itself. It will not go all over the, to the more generic supertube with the same, there's another supertube here which I can build, which is also part of the same moduli space. You'll not go from the blue guy to the red guy by just having a tiny excitation. A tiny excitation will keep you have the red guy, you ping it, it will stay nearby. It will not go all over the moduli space. You remain in the same, in a similar configuration. That's
so you would argue that if I start with some throat length L and I hit it, then I keep having the same throat length L. I'm not going to get like L plus epsilon.
Not exactly the same, maybe it will differ, but this is the way I understand these clumps here. I mean, you have a clump and in some region, and you're not going to excite all over the moduli space. You just stay in some region nearby where you started.
Well, I think it's probably more likely that you are going to diffuse across the moduli space.
No,
the magnetic field will govern the rate of diffusion.
Samir is saying you won't. That's the whole point.
That's a classical intuition.
Indeed. Right? So in the probe calculation, you don't.
And in a quantum theory, a random magnetic field you diffuse in, and the strength of the randomness governs the rate of diffusion.
Oh. But I think if you just do a probe calculation, you not see this diffusion. I'm just trying to see if there's a way to, again, if one can link this probe calculation of Samir to this calculation, to these blocks, and to this thickness, and the fact that, again, smaller supertubes, which are deeper throats, these modes become more and more rigid, so it's much harder to explore the phase space. Then it will be possible to do this calculation for the 3-charge system.
But do I understand well, Joseph, that your ideal scenario is that you kick this supertube, and then the supertube stays into the same strand number sector, and so that the length of this motion in moduli space is a proxy for the size of this band, of this block of.
I don't know, but again, I haven't done either calculation, and both Samir and Yiming are here, so that I don't know, Samir, if this is the right way to.
Yeah, I think I agree with what you're saying. I think that there are two different limits which might be relevant to Emil's comment. If you take a throat which is, let's say, fairly smooth, right? Let's take something which is the maximally rotating 2-charge or something like that. And then around that, you give a kick which is small. Okay. So then all the things that I was just saying would be true. On the other hand, you could take a limit where the throat is very deep, okay, right? Like a highly orbifolded case. And then the amount of kick you need to do to talk about this, all that I was saying, was supposed to be a small kick. That will have to be much smaller because the same size kick might become a big kick now. So I think there are these two orders of limits, right? And so once you start talking about quantum effects like Emil is talking, maybe you're talking of things which are very, very highly wound. So their winding can go to the order N1, N5. And then indeed, the notion of small completely changes because a little bit of energy and you mix with everybody else. So it could be that the protection lasts for in the classical limit, like while you have a smooth geometry with small perturbations, it's a solvable problem, and then that's what you get.
But then again, if we can make this calculation for again, supertube wrapped 5 times, and we can link it to the thickness of this, you can argue that super tubes wrap more times, they give you deeper solutions, they are more rigid, and therefore this bump is smaller. For example, or here, I mean, then
that's very nice to see. That could be very nice to see. And I think then Emil's comment would simply say that if you go like deep into the bottom right corner where the string is very highly wound, and then in that case, all this doesn't apply. And that's of course probably very, very true.
no, but then I can do another calculation in the bulk. So I can do indeed, if you go to the very wound corner, those are some states which again I cannot calculate with them, and they'll be very generic. But I can take a long throat again, and I can put the super tube at the bottom of the long throat. So I have this long throat with bubbles, which I'm not drawing, and I just put the beautiful round super tube down at the bottom here.
Yeah.
And then I'll do a calculation, which is again a bulk calculation.
Yeah.
But again, instead of having the super tube in flat space, I'll have it deep down the 3-charge throat. And then I can calculate these things. So if there's a way to relate this thickness to your ring mode, then I calculate the tallest time. Then I can calculate this tallest time for some examples of deep microstates directly in the bulk. Because I don't know how to do the calculation of the tallest time in the bulk or in the 3-charge system. So, this seems to be the cheapest way to estimate what this is.
Yeah, I think it probably should be possible, but modulo the question of how the supertube couples to the ambient supergravity in the long throat.
Oh, this is known. We have the action of the supertube. I mean, this is known. We actually did it in Born-Infeld. We did it in supergravity. I mean, this is beaten up to death. It's about 15 years ago we did it, right, Nick? It's called Born-Infeld in supergravity. So this calculation, and it's very nice actually when you have it down the long throat. You have some enhancement effects. So there's some cool physics going on when you have the supertube down these long throats. But if one could get Samir's calculation of the ring down of the supertube to be linked to this with this thickness here, then one could do this calculation. One could just say in the bulk, when you have these long throats, you'll have this, and the thickness here will be something. We can just estimate this number, and which would be a nice thing. I see that somebody sent the paper in the chat. Okay, more questions? More comments?
Sorry, this moduli space, Samir, this moduli space that you're talking about, is that this equivalent of moduli space of instantons, or is it the moduli space of the supergravity theory in the near horizon region?
Okay, let me see if I understand the question. The first calculation in that paper would be just about supertubes in flat space. Okay, so it's not the instantons or anything. There are many frames, and you can use the NS1P frame or you can use the D2, D0. But anyway, you want to look at it, it's just a tube. It's in flat space, so it's a well-defined thing. And there's obviously many solutions with the same quantum numbers. And the question is whether a small kick to the solution causes the supertube to drift arbitrarily far in this space of solutions, or it doesn't. And there the answer is very easy, because just a simple supertube in flat space, just in the classical supertube, and the answer there is it doesn't go far. It goes as far as the kick, strength of the kick, just like a Landau level, a particle goes in a circle in a magnetic field. When you turn the gravity strong, what you have is two different ways of looking at it. If you go down to the deep throat, now you just have we're just looking at throat, not in the instanton language, which is the dual CFT picture, but just in the deep throat. There, as I was saying before, the vibrations of the throat are much cheaper than actually trying to change the shape of the supertube at the cap. So the cap shape is the one which is now the structure of the supertube. We started with that weak coupling, but that's more rigid than the whole rest of the tube. And you get those graviton modes, which were not present in the flat space limit because you didn't have the deep cap. To talk about the thing you were asking about, the instantons dissolved, I think, is that what you meant? The D1 as instantons dissolved in D5? Is that what you meant by instantons?
Yes, exactly,
right.
Exactly.
So that's the brain picture. And there is a connection to that. That's the last section of that paper that I just put up there. What you find is that the transition point from having the supertube vibrations at the cheapest degree of freedom to the fact that when those freeze and the vibrations of the deep gravity throat become the cheapest degrees of freedom, in the instanton language, that happens when the cheapest fractional mode instead of becoming fractional instantons, become fractional D5 brains. So if we just talk in terms of fractional brains, which is a heuristic way of talking, which started in the old days when we were doing all the gray body factors and all of things. If you talk in terms of fractional brains, which is a heuristic, you find that when the fractional brain picture changes, like which is the lightest fractional brain in the D1, D5P brain language, when the brain changes from one type to the other type, the lightest brain, that's when this freezing of one set of degrees and the ingravity and the other set of degrees taking over. It corresponds to that in the brain picture. So there is some connection to what you said. It's a more heuristic connection because the language of that instantons is more heuristic. But that's all we had.
Thank you very much.
Okay, more comments, more questions?
Samir, in the calculation that you did, when you kick a supertube, does the configuration stay supersymmetric, or do you go generically non-BPS?
No, of course non-BPS. When you kick it is of course non-BPS. So you're making it slightly off BPS, and you're asking if that extra BPS energy will make the guide drift.
So then I guess the calculation is slightly different from what Yiming was doing, right? Because Yiming's projection. So if you could project that kick, like, correct me if I'm wrong, correct me if both of you are wrong, but like what you're doing now is you're kicking a super tube and you're making the general perturbation on BPS. But what would you like to connect to Yiming's pictures? Like you kick the super tube and you see how this sort of like evolves in the space of BPS states rather than in the non-BPS sector. Right, so you need to, there's a way in which you would need to project. So there's two questions, right? So which is the operator in which you kick it? I guess if you manage to project that kicking operator onto the space of BPS states and then see how this evolves, then this would give you a connection to the band. Otherwise, I don't know. Otherwise, this is the standard thing that we've been looking at for a while. Like this is similar to what Marov and Pum has been looking at, right? You kick a super tube and it generically goes to non-BPS states. Whereas like here, I think what you would want to look at is something which you perturb a BPS system and which nearby BPS configurations does it go to? And I guess that's the difficult thing. Like how do you find a perturbation operator which will take you from BPS states to BPS states? I don't know whether this makes sense, but I got like that was my intuition from Yiming's thing, right? You start with a super tube, you make a BPS perturbation, or if you want to make a perturbation and then you project onto supersymmetric states again.
Yeah, I mean, but I guess if in Samir's picture, even if you perturb it away from the BPS space, it is rigid, and you probably also the amplitude where it remains in the BPS subspaces has also some rigidity.
Yeah, I guess it gives you an upper bound on the right. So it's highly unlikely that it's going to be more chaotic or like more banded in the BPS states than it is in. Is that true?
Well,
you need the right effective action.
Yeah.
I think I'm just trying to grab a rough intuition from what Yiming Chen has been saying. So it's more like a question, a comment and a question. So if the guys split up into things like the guy's super tube of one shape, like just wants to stay near its shape, and the super tube for different shape wants to stay near its own shape, it looks like a StatMax system where different parts don't really want to go into each other. This part is separate from that part, and if you excite something here, it doesn't automatically couple to something which is somewhere else. If you have something like that, the eigenvalues which are coming from this region and the ones from this region, they can be of the same rough value. And so they could be looking like close by lines in what Yiming Chen was drawing, but they have nothing to do with each other because there's no dynamical connection between this part and that part. So they'll be like a Poisson distribution and there'll be no level repulsion. So is that correct? If you are seeing low level repulsion in system, is it true that I could think of that as saying that system is made of many different parts which don't want to talk to each other, so their different eigenvalues just happen to superpose on the same value by chance, and obviously there's no level repulsion because they're not cross-connected. Is that statement at all correct?
Well, I think at the first level, it is kind of the picture. If you already have like decoupled sides, then the spectrum should just be Poisson. But I think here is slightly more complicated because there's still some coupling between nearest neighbors. So eventually you have this diffusive motion across the entire system. So in these kind of situations, if you look close enough in the spectrum, you do see random matrix statistics. And the question is exactly the question is what is the Stauler's energy scale? So that lets you to quantify how strong the chaos is. And in this kind of a nearest neighbor coupling system, the chaos is not very strong.
So in fact, so just to complete what I was saying before, I think what you said is very relevant. The flat space case is not the case that you have on the screen here because you're starting with the orbifold CFT, which is not what describes the flat space supertube, right? So
works in the flat space. The calculation is just an ADSC. I mean, he calculates in the orbifold point, but then he just goes to the flat space limit. It's a 3-point function, so it gets please protected. So you can just say that he calculates, he throws a graviton on a supertube in flat space, gets an answer, and he projects on the PPS configuration, and that's the curve.
Right. So I'm not completely sure about the BPS projection part, so let me not comment on that. But the whole difference between the flat space case and the case we developed the deep throat is that when you develop the deep throat, in the language of the D1, D5P orbifold theory, the lightest excitation is that you have a D1, D5, but the lightest excitation is creating PP bar pairs. When you have a supertube, it's the analog is you start with the D1, D5 in flat space. When you put in flat space, the analog is that the supertube is made of two charges, let's say NS1 and P. But when you kick it, the energy goes to more NS1 and P. It doesn't make a third charge. It just makes more of the same. So when you transit from making more of the same two charges to making a third orthogonal charge, like PP bar as opposed to just the D1, D5 you had, that's the transition. So I think all these graphs which are being drawn are drawn for the theory where you've already transited to the other side. That is, you have D1, D5, but if you add a little energy, you'll create a PP bar. So that's not like the flat space supertube. And so the whole transition we were studying was, when do you take a two charge system, give a small kick, and the extra energy goes to more of the same two charges, as compared to when you give something an extra kick and it goes to a third charge. So I think all these graphs are in the domain where you have taken a theory where you go to the third charge. And that crossover is what this paper is trying to bring out.
I see. So then, but then Yiming's calculation is when you go from a two charge to a two charge, because I mean he's projecting on two charge states.
Yeah.
Yeah, so that extra PP bar excitation is,
Yes.
as Chipak was pointing out, it's slightly outside the maybe
Yes.
domain of this, but morally it may be connected.
I see. Very nice.
Right. I'll try to read more and think about it. It's very interesting, this connection to gravity. Very interesting.
Okay. More questions?
Maybe just a follow-up on all the things that were just said. So this was very informative, this discussion, so thank you. And let me just say a few words about this graph you have here, and you can tell me if I'm reading it now correctly. So this block you're showing us is when k equals 8, so that means number of cycles is 8, and capital N is 30. So average length of the strand is something like 4. So we have 3s, 4s, 5s in the distribution, which is fine. We're working with concrete integers, and these are transitions from something like 8 strands to something like 9 strands. So
or 7 to 8,
or 7 to 8, but something nearby. So just in terms of Samir's questions about how far away this supertube is going, we're going to cut or join some things which are 3, 4, or 5 into maybe a cut into something which is 2s and 3s, or a join into something which may be 8s or 9s or something like this. So that we're changing the harmonic, the Fourier power of the supertube configuration, but not by a lot, because most of the strands are not getting cut or joined in the process, and this is because you're just in terms of the probe, it's like an L equals to 1 graviton, because the twist degree is 2. So you're putting in a graviton with very low SU2 principal quantum number on the S3, and so it gives in that sense just a small kick to the supertube. Is that correct so far?
Yes, I think so.
Yeah, and then I think the questions about whether you get PP bar excitations or how the thing settles down, I guess cycles a little bit back around to this coefficient CL1L2, which describes how likely you are to actually get a ground state when you throw in such a graviton, which is fairly, it's order 1 likelihood when L1 and L2 are order 1, but when L1 and L2 are large, you're less and less likely to actually get a ground state, and you're more and more likely to excite some excess energy, which would have to then re-radiate away.
Yes, that sounds exactly right. Yes.
Okay, thanks.
Thank you for the clarification.
So actually, I have a question. If no one is, so the question is, in your definition of the Fowler's time from the spectral form factor, for example, the one when you average over the card shuffling, I just heard that recently that there's somehow some people who differ to the in the definition of how to define the Fowler's time. What if you define the Fowler's time to be the minimum of that curve? Would that change something? Would you have found that the Fowler's time could be of order 1 instead of order n to the power alpha?
Well, I mean, I don't know the motivation of that definition, because like there are many body examples where after the initial decay, it goes up and then does something and eventually goes to linear ramp. So if you define it as whenever it first dips and then goes up, that like the physics it's not clearly related to where the ramp starts. So I guess I wouldn't call that the Fowler's time. Maybe there are some other reason to define that quantity.
Yeah, okay. I just heard about this debate, but I don't know. I don't know so much about it, but I can tell you more.
Yeah. Okay. Yeah.
I just heard that Yudan Zona was not agreeing with this definition, but I do not know exactly what he had in mind. So yeah,
I see.
But thank you.
Yeah, it might just be a terminology issue. Yeah, I guess.
Okay, so if there are no further questions, let's thank again Yiming and all the participants. This is really the way I want the conference to be. So again, 1 hour talk, 1 hour discussion. This is
that's really...
If we can get all the other talks during this micro conference to be like that, I'll be ecstatic. And Yiming, when you pass by Europe again, we organized this conference. We decided last week. So this is really hastily put together. Normally we would have invited you to come over and so on, but it was just very hastily put together. So thanks a lot for doing this, and thanks for waking up so early. So
Okay, thank you so much. It's great discussion. Okay.
Yeah, great. See you guys. Bye. Bye.